Welcome back to BE 110. Today we're going to continue our discussion of kinematics by considering the tensor quantities that we need to understand and describe flows, which are the velocity gradients, the rate of deformation tensor, and the spin tensor. So much in the same way that to consider shape change, we considered the gradients of displacement, since displacements alone could just be a rigid body motion. Well, we do the same with velocities. If every point in the fluid had the same velocity, then the fluid really wouldn't be flowing. It would be like a milk truck driving along the freeway. Every particle in the milk would have a constant velocity, but the milk wasn't actually flowing. It was just undergoing a rigid body motion. So in the same way that shape change requires gradients of displacement so that lengths will change, flows require gradients of velocity. So now we can consider an element of a velocity vector dv related to an element of position vector dx through a tensor L, and the components of that tensor from the chain rule of calculus would be del vi, del xj. And this tensor L is called the velocity gradient tensor. Like the deformation gradient tensor, there's no requirement or expectation that it be symmetric. In general, it's not symmetric. Unlike the deformation gradient tensor, we can decompose it, but not through the polar decomposition theorem, but rather through the simpler additive symmetry decomposition. So we decompose L into a symmetric part and a skew symmetric part as follows. So L will equal a symmetric part, which is 1/2 of L plus L transpose, plus a skew symmetric part, 1/2 of L minus L transpose. And the symmetric part is called D, the rate of deformation tensor or the strain rate tensor, and the skew symmetric part is called W, the spin tensor. So therefore the components of D will be 1/2 del Vi del xj plus del Vj del xi, which looks very similar to the Cauchy strain tensor with V instead of U. And in fact, the components of the rate of deformation tensor are often also referred to as the components of the strain rate tensor. So we see that D is a linear expression, there's no quadratic terms, and it's equivalent to the time derivative of the linear Cauchy strain tensor. In other words, since Vi is del Ui del T, and epsilon ij, the Cauchy strain tensor, is 1/2 del Ui del xj plus del Uj del xi, then that means that Dij is 1/2 of del Vi del xj plus del Vj del xi will be the same as del Eij del t, or in tensor direct notation, D is equal to epsilon dot. The components of W are 1/2 del Vi del xj minus del Vj del xi, which is skew symmetric. And these are called the components of the spin tensor. The spin tensor W is related to another useful quantity called the vorticity vector, lowercase w, which is defined by the curl of the velocity vector. So W is equal to curl V. Or in index notation, Wi equals Eijk del Vk del xj. And so we can show that the spin tensor, capital Wjk, its components are related to the vorticity vector by minus 1/2 Eijk little wi, and the inverse of that relation is little wi equals minus Eijk capital Wjk. So to prove this, we need to use the E delta identity that we introduced earlier. Now, the way that we wrote the E delta identity was EIJP ERSP equals delta IR delta JS minus delta IS delta JR. We need to rearrange this to put it in a form that's more useful for us. So we're going to recall that cyclic permutations of E are the same. So if we'll cycle P to the front of this expression of each of these, then we'd get EPIJ times EPRS must also equal delta IR delta JS minus delta IS delta JR. And now we're going to substitute J here for I, K for J, L for R here, P for S here, and I for P here. So the same expression, just using different set of indices, will become EIJK EILP equals delta JL delta KP minus delta JP delta KL. So now we can use this version of the E delta identity to expand our expression WJK equals minus 1/2 EIJK little wi, using the definition of little wi as EILP del VP del XL. So this will now become WJK equals minus 1/2 EIJK times EILP times del VP del XL. And now we'll use our E delta identity, and this product will become minus 1/2 delta JL delta KP minus delta JP delta KL times del VP del XL. Now expanding this out, we'll get minus 1/2 delta JL delta KP times del VP del XL minus delta minus 1/2, so plus 1/2 delta JP delta KL times del VP del XL. This turns L to a J, P to a K, P to a J, and L to a K to give us minus 1/2 del VJ del XK minus del VK del XJ, which is our original definition of the components of the spin tensor. So this is the result that we wanted. We've now proven this expression relating the components of the spin tensor to the components of the vorticity vector through the permutation symbol E. So in class we'll see some examples of these different tensors and the vorticity vector and the kind of flows that they apply to.